Two-dimensional collisions. In a two-dimensional collision, objects are moving in both the x and y directions. You'll have to solve for each component of the momentum in x and y. Each object's individual momentum can change, but the total momentum cannot. Therefore, we can say that in the x direction, the total momentum is conserved, and in the y direction, the total momentum is conserved. In this picture right here, that makes sense because you can see the initial object has a rightwards momentum, meaning that the objects after both have rightwards momentum. You can see that the initial object does not have any up and down or y momentum, which means that the y momentums after have to cancel. That's why this object moves up in the y direction and this object moves down in the y direction. In order to solve these problems, you first have to set up a coordinate axes, x and y. Sometimes, though, your objects are not moving in the x and y direction you anticipated, like this guy right here. If this guy were moving in the x and y direction, you'd have to draw like an angle like that. And that would suck to do for each of these objects. So you can actually define your velocity with respect to your own axes. That means that when you're solving the problem, that you can make this x and this y and like tilt your whole axes over. You can do that. That just means that you have to be consistent with like this guy too. This guy would also have to have that same set of axes. If your object's velocity is not along those axes, you'll have to use trig to break them into components. I find it easiest to draw a before and after picture labeling all velocities and masses. And I'll show you an example in this next slide right here. We start off with ball A rolling west at a velocity of 3 and a mass of 1. Ball B has a mass of 2 and is stationary. This is our before. So it says afterwards, ball A is moving south at a rate of 2, and ball B has an unknown velocity. This is somewhat unrealistic because in real life, this object could not move straight down. But I think that this is illustrative of an interesting like math problem. So even though it's not realistic, I'd like to show you how this math works. We're going to start off by finding our total momentum in the x direction, remembering that momentum is mass times velocity. So we're going to find the total momentum by adding together the mass and velocity of these two, noticing that since this object's velocity here is to the left, that means that it is a -3. And we'll set that equal to the after. We don't know the velocity of object 2 after, so we'll leave that as our variable. And this object right here has no xwards velocity after, so we'll put it as 0. In the y direction, this object is moving downwards, which is why its velocity is -2. I will solve for the velocity in x. And then I'll solve for the velocity in y. So that means that our velocity in x is negative, meaning it's going this way. And our velocity in y is positive, meaning it's going this way. And we can find our total velocity using our Pythagorean theorem. Our total velocity is 1.8. It makes sense that our total velocity is moving in this direction because in the x direction before, it's moving to the left. So afterwards, it needs some leftwards momentum. And in the y direction, there's no velocity before. And after it's moving down, which means that there needs to be an upwards to cancel it out. So therefore, it makes sense that our answer goes to the left and then up. Let's try our next example. Setup is the same as the last one before, but afterwards it says ball 1 is moving to the left at 2. It's slowed down a little bit. So now we're still looking for the velocity of this guy. I'll break it up into our x and y components. Here's our x component. And in our y component, neither of our objects are moving. So in this direction, our velocity is 0. But in the x direction, our velocity is -1/2. So that means that our velocity is -1/2 in the left direction, and there's no velocity up or down, so that is our answer. Next, we're going to try an inelastic collision. The first car is moving east at 45. The second car is moving north at 30. Afterwards, they collide together. I like to draw that kind of like as like a dust cloud to show like the boom of the explosion. So afterwards, their masses are going to combine, and it's going to be 2,500 with an unknown velocity. So let's set it up in the x direction and the y direction. There we have x, and let's do y. So in both situations, I solve for a velocity of 18, which means that our total overall velocity is to the right 18 and upwards 18, giving us a total velocity of 18 root 2, 25.5, at an angle of 45 degrees this way. Nice. Let's try our next one. We have 2 hockey players, one with a mass of 82 skating north and one with a mass of 70 skating east. They move and collide together into like a big squish right here. Their total mass together is 152, and they move off at a velocity of 3.5 at an angle here of 67 degrees. And we want to know, what were their initial velocities? Let's check that out. We'll split it into x and y. And we'll make sure that their velocity after is this part of the triangle right here. And for the second half, it'll be the upwards part of the triangle here. So for the first guy, the 70 kilogram guy, I got a velocity of 2.97 meters per second to the right. And for the second guy, I got 5.97 up. Nice. All right, last example. Object A is moving to the right at 2 towards object B. They collide, and this is their collision after. You can see afterwards, this object is moving upwards and to the right. This object is moving down and to the left. Oops, this shouldn't be here. This is unknown. Okay, an important thing to realize in this problem is that this x-axis right here is not equal in terms of velocity for both objects. That means that this object's leftwards component right here is not necessarily equal to this object's leftwards component right here. They will together equal up to 4, but they will not both equal 2 and 2, for example. Let's take a look. In the x direction, we have an object of 2 moving at a speed of 2, an object of 4 at rest. Afterwards, this object with a mass of 2 is moving at a velocity of 1.1 cosine 30. And this second object down here has an unknown velocity. Let's do our y component, making sure that we say that it's the sine of 30 to represent this part. Let's solve for the velocities of our second object. I got a velocity of 0.525 to the right. Next, in the y direction, I got a velocity of 0.275. Oh, it should be negative 0.275. That means down. So that means that if we are looking at our total velocity of this guy right here, that this guy's total velocity should be 0.525 to the right and 0.275 down, which gives us a total velocity of 0.592. Nice work, guys.